We have a vehicle here that the customer complains that the car will not run if it stays parked overnight. The following day, the car will not start unless it's jump started. They were suspecting either a bad battery or a bad alternator. This battery is fairly new. It has been recently replaced. We checked the battery. The battery was low in charge. We fully charged the battery, load tested the battery afterwards. Battery passes its test. We also checked the alternator. The alternator is putting out 14.5 volts when the engine is running, and it also provides the right amperage if we load test the alternator. So it's not an alternator issue, it's not a battery issue. So we might have what we call a battery parasitic drain. That means something stays on when the vehicle is off. Something's not shutting off, or something is shorted that's causing current flow. So we need to measure that current flow. We are going to measure this current flow using different tools. First, we're going to use a multimeter, and we're going to measure how much amperage is flowing through the circuit. Right now the vehicle's off. It's been off for at least an hour, and we do have current flow, so we're going to verify. In order to get a measurement, we're going to use an amp clamp. Now the amp clamp will be used as an adapter for the multimeter. The amp clamp has a red and a black connector, which we're going to connect it to the volts and the common connector. We are going to set the multimeter in millivolts, and once we turn on the amp clamp, we need to zero out the tool first, because right now it's giving us a measurement. So in order to zero out the tool, we have a rotating knob here on the amp clamp, and what we could do, we could just rotate it until our meter measurement goes down to 0. If we go too far, it might go to the negative side. See that negative? So it kind of bounces back, and there it is at 0. So once the tool it's zeroed out, we're going to hook it up on the negative side of the battery. Now, and we're getting a measurement of 2.4 millivolts. So what that means, every millivolt represents an amp. So this is measuring 2.2 amps that are flowing on that negative side, and the vehicle's off. So around 2.2, 2.3, kind of fluctuates up and down. So that's our measurement. So we do have a parasitic drain, which will drain your battery. So we need to find that problem. We need to figure out which circuit is staying on that is causing this drain on the battery.
Maximum is 50 milliamps for most vehicles.
Let's hook up an oscilloscope as well. Here we have an oscilloscope that is currently measuring 0 amps. We're also going to use it with an amp clamp. We're going to turn on the amp clamp, and we're going to zero out the tool. So you're going to turn on to the lowest setting, which is 20 amps. We zero it out. Once we zero it out, once we press this button that says 0, you're going to see a line fluctuating or moving up and down as a response to the meter. So once we zero it out, press the button, so it kind of goes up and down. So that means it's all set. So we're going to hook it up as well. This amp clamp has an arrow for polarity. That arrow is going to be pointing towards the battery, because the current flow flows from positive to negative. And there's our measurement. If I have the amp clamp the other way, there is a measurement, but it went down to the negative side, negative 2 point something amps. So in some cases, in some scopes, you would not be able to get a measurement until it's properly it's on the proper direction of current flow. So we flip it over, and you can see that we also have a 2.2 or so amps. There is current flowing. So you can see the difference that an oscilloscope, an expensive tool, can give you the measurement same as your multimeter. So the amp clamp can be attached to a different type of meter. It doesn't necessarily need to be a fluke meter. Let me give you an example. Here we have another meter. This is a Matco meter. We turn it on into millivolts. Make sure that the setting is in DC volts. We hook it up the same way, but we need to unplug it so we can zero it out. And we got a 0.0302. We kind of move this knob. Notice that if I go too far, it starts to increase. So we zero it out as much as possible. Went a little too far. It's very sensitive. There it is. So we hook up the amp clamp, and we're getting the same exact measurement. So you can always use an amp clamp as an adapter. Every millivolt represents an amp. So we have 2 amps and 190 or 210, kind of fluctuates at 210, 220 millivolts. So that's 2 amps, 200 millivolts. And it's the same measurement that we have with the scope. Now, we have verified that current is flowing. We have verified that we do have a drain. Now, the main thing is, how do you find out where the drain is? How do you isolate a circuit or a system that is staying on? What you could do, there's multiple ways of running this test. Some will ask you to pull out a fuse, one individual fuse at a time, and watch the meter. So whether you're using a scope or you're using a meter, let's say we just focus on the meter. Every time you disconnect a fuse, you want that measurement to go down to 0. That's what you expect to see. But the problem that I have with that test is that if you pull out a fuse that powers up a PCM, a TCM, or a BCM, which are modules, if you disconnect the fuse that powers up a module, the module could go to sleep, and you might not experience the same problem if you put the fuse back. What we expect to see is that every time you remove a fuse, amperage should go away. If the amperage goes away, you found the circuit that it's staying on. If not, you put the fuse back on, or you can leave the fuse out and go to the next one until you find the fuse that takes the amperage away. That tells you that is the circuit that is staying on. But the problem I have with pulling out a fuse is if it's a computer causing the problem. You pull out a fuse, amperage goes away, you put it back on, amperage stays away. So you might think, well, the problem is gone. But no, that means you might have to end up starting the car. In some cases, you might have to drive the vehicle so that computer could start to operate like it should under different conditions, and then it might take a while for it to not go to sleep or not go to sleep at all. So one of the tests that we're going to do to find this issue, instead of pulling out fuses, we're going to be using a multimeter to perform voltage drop testing. Every time current is flowing through a circuit, there will be a voltage drop measurement in a fuse. We will use a voltmeter. We are also going to use an infrared thermal imaging gun to try to see if we could find the problem. Now, this is going to depending on how much current flows through a circuit. If it's enough current, we might be able to see it with a thermal imaging gun. But if not, the multimeter, it's more than enough. But we'll compare to as well. I just want you to know that we do have different types of tools that we can use to figure out a problem. Whether you have a scope, a meter, whatever tools you have access to, as long as you know what you're looking for, it'll be helpful for you to find the problem. Let's start by performing voltage drop testing at this fuse box. All right, we are going to start by performing voltage drop testing on fuses. So the way you're going to run this test is you're going to set the multimeter in volts, millivolts. Select the millivolt setting, not the volts, the millivolt setting. And you see that number right now is fluctuating. So as I move my leads, numbers will fluctuate, but once it's steady, you will get a measurement. So if we get a steady measurement, like for instance right now, you get 0. Voltage trying to fluctuate, so meter is in auto range, is trying to figure out the range of the measurement of the voltage. So all we have to do is just perform a voltage drop test across each fuse. What we're looking for, ideally, we want to find 0 millivolts across every fuse. But the one that gives you a measurement, there is a problem with that particular circuit. And then we could find out on a wiring diagram to see what that fuse is powering. So let's start with this column here. Put the meter across. We get 0. Next one, 0. 0. 0. Notice every single one is giving me 0 volts. There we have measurement there. That it's 0.1. That is 100 millivolts. We'll see what that is powering. Got another one, 0. 0. 0. 0. We're getting 0. So you go through every fuse. Now this type of test will be time consuming, especially because in some vehicles we might have more than a fuse box, than one. Some might have multiple, more than one. Got 0. There it is, 0. Let me just verify it. 0. Let me go back to the first, the one that got a measurement. That was 0.1. And we got a, let's see. Oh, we got a 0. So 0 volts on all of them. We also have more fuses here. You're going to go across every single fuse until you find the source of the fault, if there is a problem. We got 0 there. 0. Let me just double check. Now if I fluctuate, I want to make sure it makes good contact. There it is, 0. See, I don't make good contact, meter readings will fluctuate. There's another 0. And we got a 0. We also have other two fuses. Those are cartridge fuses. We can also perform a voltage drop there as well. But we're going to check the inside fuse box as well. Now, if we use our thermal imaging gun, we can also see that not a single fuse is hot. There is no current flowing. So we could also look at the other two. The ones that we don't have access with the meter right now, I can't really do a voltage drop test until I remove the clear cap, but you just have to be careful not to break it. So I have to be very patient on it. But if we put a thermal imaging gun, I get no sense of heat. So there is no current flow on this fuse box. Also, you can also use it for relays. What if a relay it's stuck on the on position? The switches are on the relay are on. You will see the relay getting hot. That was not the heat. See, I could put my hand over so you could kind of sense it. There's no actual heat in any of these relays or fuses. Now we're going to go to the inside of the vehicle because we also have another fuse box in there. We're going to check the fuses inside the passenger compartment. We have another fuse box here to perform that voltage drop test. The only thing you have to be aware of is that if we have a door open, computer will wake up and it could turn on your accessory lights. So if we look at this door here next to our door panel, it's currently on, so that's why you saw an increase in amperage when we opened this door. And then we have to wait for the computers to go to sleep. So watch what we're going to do right now. We're going to close this latch. There's a switch in this door latch, so we're going to close the latch, and that will send a signal to the computer indicating that the door is closed. And you will see sometimes if the door stays open, computer wakes up, but if it stays for a while, it slowly goes to sleep. And if we close the door latch, you will see a voltage increasing. See the light turn off, but at this point, computer network, it's awake, and then slowly starts to go to sleep. So that means we're gonna have to wait a few minutes for computers to go completely to sleep, maybe at least 10 to 15 minutes before we perform the test. Once we perform the test, you should be okay to start checking out the fuse box. All right, so now we're here checking the fuse box inside the passenger compartment, and we're gonna start checking the fuses. We're gonna check the first column, then we're gonna move our way to find out which one's fused. Just like I said, this test is time consuming. Just be patient until we find a voltage reading. So we're checking the first one. It's a 25 amp fuse. The meter shows 0. Next one, zero, 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 I have a reading there, 0.3. Let me just confirm it. No, 0. Okay. Next one. 0, 0, 0, and there's a reading here of 10.1, goes up and down, 9.3, 8.3. That is 1, 2, 3, 4. Let me double check. No, false alarm. You want to make sure you make good contact. Look, as you can see, I'm making good contact. So it's 0. That was a false alarm. Next one. Make sure it's making good contact. 0. So we're going to go through third column. 0, 0, and there's a reading here, 2.6. What is that reading? Let's confirm it again. As you can see, I am touching the 2 leads, and I'm getting a 4.8 reading. So we do have confirmed that that fuse has a voltage drop measurement. We could go ahead and do the rest ones as well. Now if we look with our thermal imaging gun, you can see that there is more heat in that one fuse. The fuse that has the voltage drop is the one that's a little bit hotter. So the thermal imaging also helps you to figure out where you have a problem. Multimeter works great. The multimeter would not fail you, but as you can see in this one, the thermal imaging, we can find the same problem. The other fuses are cold, as much, not much of a detail. Picture in picture shows a little bit of heat through the camera. Doesn't, there it is, there it is, you can see it. Visible light, you don't see anything. But you can see it through here. All right. See if I get it closer. It's only that one section. The fuse that we removed and brought the amperage down was the interior lamp fuse is a 10 amp fuse. That was the third fuse on the third column. But did you notice that the amperage did not went all the way down? It only went probably like halfway. So there is something going on here. This could be the main source of the problem, but it could at least send us to another area. But let's find out how much amperage was actually flowing on that circuit. If you recall, the voltage measurement that we had was 4.8 millivolts. So here's a chart for a mini fuse type. This is a fuse voltage drop chart. The measurement that we had was 4.8. 4.8. The fuse rating was a 10 amp fuse. So if we come down here and reference this chart, the 4.8 comes all the way down here to the 647. That means that circuit is drawing 647 milliamps. The max allowed on most manufacturers is 50 milliamps. So this is way up there. So let's find out what this circuit is powering, and if something else is connected to this circuit that could be preventing from shutting down completely. Here's the electrical wiring diagram. The interior lamp fuse, 10 amps. This is hot at all times, and if you look at this diagram, it's connected in parallel with the trunk lamp, glove box lamp, and if we follow these two wires, green and red, let's follow the red one. It goes to the driver lamp and the puddle lamp. That's the driver smart key outside the handle. Those lights are not on. The green one goes to the passenger smart key and the passenger door lamp. Visually they are off, but that doesn't mean it could be causing an issue. And here's another wire. The red wire goes to another page, terminal number 2, red wire. This is the other page, terminal number 2, red wire. This is connected in parallel with vanity switches, and this is a junction connector which is splicing all these wires together to power up the rear passenger lamp, and is powering up the left rear passenger lamp. So how are we going to figure out what's going on? Here's what we could do. We're going to access each one of those loads and probably disconnect them or make sure that they're not on. My suspicion here are these two in particular, because the other lights we could visually see them because we have access to the passenger compartment, but we need to open the glove box and open the trunk, but we also need to close the switches to make sure those lights actually turn off, or they actually are off. So we're going to find out what's going on. Here's a glove box light. It's on, and if we try to see it and close it slowly, I want to see if that light turns off. Right there, light turns off. Open it so we can see this light. It's actually turning on and off, so that tells your switch actually works. So this light does not stay on. So now let's go to the trunk. Here's the trunk light. I'm going to remove the light bulb itself so we can kind of have access or visibility to look at the light as we engage the switch. We have the trunk open. It's normal for the light to be on because of the latch. There's a switch here in this latch. If we just close the latch, we should be able to see the light turn off. So right now it's currently open. If we close it, right there's closed, there's no change. Now if we open it again from the back, there it is, open and close. If it's closed, the light stays on. So here's the problem. There's a switch on this latch. Let's find out what's going on there. All right, let's start removing this cover so we can access the latch. Careful not to break those clips. And there's our door latch. So first thing we're going to do, if you suspect that this is our problem, since the light is not turned off, we're just going to unplug it. We're going to unplug it. If the light turns off, we know that the latch has a problem. So unplug. There's a clip on the back. There it is. Unplug. Now we plug it back in. As you can see, there is a change in the light. So we definitely have a problem with this latch. Alright, we were able to replace the door latch, and now let's see its operation properly. As you can see, the light is on right now because the trunk is open. But once we close the latch, the light should turn off. Just like that. Now we open it. Turns on, off. Before, there was no change. Now we have verified the problem. It has been successfully repaired. Let's see how the system operates. The lamp fuse supplies voltage to the trunk lamp room. The IPS control module grounds the circuit, allowing the light to stay on. And now the reason that's happening is because we have the trunk room lamp switch that it's staying closed at all times, and that will send a ground to the IPS module. Then the IPS module will control the circuit, allowing current to flow. But when the fuse was removed, why did the amperage did not go all the way down, as you notice here? The reason why is because the IPS control module, it's a computer that has to communicate with other computers through a communication network. So the IPS control module will stay awake and will try to communicate with other computers within that network, and it will not allow the bus network to shut down, causing other computers to stay awake. It could potentially draw current as well. So this is after the repair. As you can see, it's fluctuating around 60, 70 millivolts. System is completely shut down compared to 2.2 amps that we had previous. Most manufacturers will allow you up to 50 milliamps of current draw when the vehicle is off, but always look at manufacturer specifications because some might be slightly higher. That's why you always look at specs first before you determine if it has a drain or not. So this is after the repairs. We completely started shutting down, and the amperage is going down to 60, 50 milliamps and slowly going down. Big difference than where it was normally at.